So very good evening to all the students who have joined the session. We will wait for a few minutes, for 2 to 3 minutes, and then we will start the session. So can someone type in the chat box if my slides are visible and my voice is audible? Just write in the chat box if it is audible and it is visible also. Okay, thank you so much. Now we will wait for 2 to 3 minutes, then we will start today's session. So let me introduce myself first. I am Moshumi. Somebody wants to join. Okay. So I have muted your mics, and so there won't be any network issues throughout the session. If you have any query, any doubt, you can write in the chat box, and at the end of the session I will answer all the queries. So let me introduce myself first. My name is Moshumi Deb, and I am the PMRF Fellow of Department of Chemistry and Chemical Biology from IIT ISM Dhanbad. And this is the week 2 live session, problem solving session for the course Organic Chemistry in Biology and Drug Development. We will try to solve some few 10 to 11 questions today, just like previous week. Today's content is basically based on the week 2 videos, which are the lecture 5, 6, 7, 8 and lecture 9. So about this, from these 5 lectures I have made some relevant questions, and the questions we will solve together today's class, and this will help you for doing your assignments which you have to submit for your week 2 session. So we will wait for 2 more minutes, and then we will start solving the questions. Again, I am saying, if you have any doubt, any issues, you can write in the chat box. At the end of the session I will answer the queries, or if you have any more doubts, you can also mail in the discussion forum, and I will answer that in that discussion forum. So let's start today's test session. If anybody joins, I have to just let him or her entry. So okay. So yes, the first question, it says that which of the following reagents are not used for the protection of the amine group. Now this amine group, it can belong to any amino acids, any peptide, the free inside of the peptide, or it can be any amine group for any organic molecule. So the options are as follows. The first option is 9-fluorenyl methoxycarbonyl chloride. Option B is tertiary butoxy carbonyl anhydride. Option C is benzyloxycarbonyl chloride, and option D is dicyclohexyl carbodiamide. So to answer this kind of question, I have given you options for the names of the reagents, and if you have the when I have seen that when the formulas are given or when the short forms are given, the students can answer this type of questions very easily, but when the names are given, they sometimes don't know how to answer it. That's why I have given the names for the question. So yes, so the question is which of the following reagents are not used for the protection of the amine group, and let me show you the answer first. So the answer is D, dicyclohexyl carbodiamide. Now I will show you the structure of all these 4 reagents. So this is the FMOC protecting group of amines. FMOC stands for the first option A, which is 9-fluoronyl methoxycarbonyl chloride. Now this is the structure of FMO chloride, and this group is basically used for the protection of the amine site. Now the second option is tertiary butoxide carbonyl anhydride, and this is abbreviated as TBOC protecting group, and this is the structure of this TBOC protecting group, the tertiary butoxycarbonyl anhydride. Then option C, it says that benzyl oxycarbonyl chloride, and this is the structure of this benzyl oxycarbonyl chloride, which is commonly known as the CBZ protecting group. And the last, which is not our which is our answer, like dicyclohexyl carbodiamide, it is the very known reagent, DCC reagent. It is not used for the protection of the amine group. It is basically used for the synthesis of the amide bond from a carboxylic acid and a amine. So I will briefly discuss how it doing. Now as you can see that there is a very common group like this. So there is a very common group. I will show you the answers first. Yeah, very common group like this OC double bond OCl, and this group basically helps to protect the amine group, which is the free amine group. Now how it's doing, the mechanism you will also get from the books or the lectures, just remember that this is the name of this protecting groups, and this DCC is not a protecting group. It basically only helps to synthesize of the peptide moiety. Now moving toward the second question, now how it does that, I will show you briefly that there is a lone pair of this amine group. Now this lone pair will attack in this site of this carbonyl carbon, and this will do the resonance, and chlorine as a living group it will just remove, and we will have something like this structure, and that is how it protects the amine group. And similarly, when there is a TBOC protecting group, it will the NH2 group, it will the lone pair of amine, it will attack here, and similarly it will attack here, but here there is no site where it can attack, so it is not a protecting group. So I hope there is no doubt in this question, and if you have any doubt you can always write in the chat box. I will answer that at the end of the session. Now moving toward the next problem. It says which of the following reagent is used for the reprotection of the benzyl ester protected carboxylic acid group. So I will first draw the structure of the benzyl ester. So basically benzyl ester means the ester of a benzyl alcohol. Now any carboxylic acid group, this is the structure of benzyl alcohol, and if there is a carboxylic acid like this carboxylic acid may be a free carboxylic acid, normal organic, or it can be the free carboxyl side of the C-terminal C-terminal side of the peptide bonds. Now how this happens, this OH group and this H group of alcohol, they react, they remove as water, and the benzyl esters are formed. So this is the structure of the benzyl ester. So this, by forming this ester bond, the carboxylic acid group is protected. Now so for the deprotection, which kind of reagents is used? Somebody wants to join. So yeah. So the answer is the palladium carbon, and supported, and it is the hydrogen is the hydrogen is the reagent which will reduce this group, and it will react and it will deprotect. So there will be, so you need to remember few reagents of when you are reading the deprotection chemistry, you need to remember which group protects which group and what is the reagent which is used for the deprotection. So you don't need to remember many of them, but there are few reagents which you need to remember for answering this kind of question. Since there is a amine group and a carboxylic acid group present in the amino acids, you just only need to remember which protecting groups are used to protect the amine groups and which are the reagents which are used for the reprotection. Like in last question I said about FMOC protecting group, TBOC protecting group, CBZ protecting group. You have to remember that these groups used to protect the amine group and which are the reagents which are used to deprotect this kind of group. Like some base like piperidine, it's used for the protection of the FMOC protecting group. So like this. And for the carboxylic acid group, there are a few reagents. You just need to remember those reagents, which are the and for what are the reagents which are used for the deprotection. So for this kind of questions, if you remember some, you can easily answer these questions. Now moving toward our next question. If you have any doubt, you always can write in the chat box. I will answer that at the end of the session, or you can email me about the questions in the discussion forum. Now this question says, identify the correct structure of the Sanger's reagent and Edman's reagent. Now you have to remember these few reagents like Sanger's reagent and Edman's reagent and what they do. So basically the Sanger's reagent and Edman reagents, these are used for the detection of the N terminal of the amino acids. There are some their functionalities in these reagents which reacts with the free NH2 group of a N terminus. Now as you know about the peptide, if it is a peptide moiety, there is a N terminal where is a free NH2 group, and there is a C terminal where there is a COOH group, and in between there is a lots of amino acid which have a peptide bonds, and the peptide bonds look like something like this. Yes. So this Sanger's reagent and Edman's reagent, they used to tag this free NH2 group. After reacting with the free NH2 group, when we hydrolyze, we will have a derivative from which we can know what is the N terminal amino acids. So first I will erase this. So just you need to remember the structures and the names of the this kind of reagents, so that you can answer this kind of question. So these are the options, and these are I will show you the answer first. Yes. So the answer is 1 and 5. 1, it is this is the structure of for the Sanger reagent, and this is the structure for the Edman's reagent. Now I will show you again. So yes, so this reagent, it is called 1-fluoro-2,4-dinitrobenzene. It is called the Sanger's reagent, and it is the phenyl isothiocyanate. It is called the Edman's reagent. Basically these two reagents are used for the tagging of the free NH2 group of the peptide bond, and after reacting with the free NH2 group, after hydrolyzing, we will have something like this 1-fluoro-dinitrobenzene, and it will, I will show you one just little bit of there is a NH2 here for the free N terminal of the amino acid, and this will react, this lone pair will attack here, and there will be some resonance, and this fluorine will be removed. So we will have something like this. Here will be NH2 will be attached here, and after the hydrolysis we will have something which is the free N terminal attached to the Sanger's reagent, which is called the DNP derivative. And similarly the phenyl isothiocyanate Edman's reagent will also react with free NH2 group, and it will, we can also detect the free NH2 group from this reagent. So just remember the structure and the names of the reagent and what they do. You don't need to remember the detailed mechanism for this reactions. And there is one more reagent which is called dansyl chloride. Dansyl chloride. So that dansyl chloride, it also it is a naphthalene derivative. Basically it also used for the tagging of the free N terminal amino acid which is at the N terminal. That amino acid used for the tagging this dansyl chloride. So just remember these three reagent, Sanger's reagent, Edman reagents, and dansyl chloride, their structure and what they do. So they do, basically they can isolate the N terminal amino acid, and we know that from the derivative which is the N terminal, and that's how the sequencing of the peptide chain is happened. So moving toward the next question. The next question is, the cyanogen bromide is specific for breaking the peptide bond associated with which amino acid? So the options are arginine, methionine, histidine and proline. I will first draw the structure of cyanogen bromide. So it is very easy structure. There is a cyanide group and there is a bromine attached to it. So cyanogen bromide, basically the structure is like this: bromine, it is attached with a carbon and it is a cyanide group. So this is the structure of the cyanogen bromide. Now I will show you first the answer, then we will discuss the mechanism. Yes. So the answer is methionine, and the why cyanogen bromide reacts with methionine and breaks the peptide bonds associated with it. We can answer this type of question if we know the detailed mechanism of the reaction. So this is the mechanism. You don't need to remember the detailed mechanism, just remember why it is happening. So because for by remembering only the names, it is sometimes it is critical. So if you just remember few little things about this structure, this mechanism, you can easily answer this. So yes, this is the structure of cyanogen bromide, which I have drawn here also, and for this is the structure of methionine. So this is basically a peptide chain where there is a C terminal amino acid, middle amino acid, it belongs to the methionine there, and there is a N terminal amino acids, and it goes like this. These are not terminal, there are all more amino acids here, it is just a fragment. So when the cyanogen bromide comes, it reacts with the sulfur of the methionine. We all know methionine and cysteine, these are sulfur containing amino acids, and for the methionine the side chain is like this, SNE. So this sulfur, it reacts with the carbon atom of the cyanogen bromide. Now why it reacts with the carbon atom, not the nitrogen? So the reason is lies in the very basic inorganic chemistry, which is the Hartsoft acid base principle. The sulfur group, it is very soft, and the carbon end of the cyanide group, it is also soft. So the soft means that you can also read it from an inorganic book. Just remember, it is soft because it is more polarizable. The nitrogen is more electronegative, so the electrons are more polarized toward the nitrogen, and this carbon is the softer side. And sulfur is also a soft center, so it will interact with the carbon, and bromine being a good living group, it will leave. So this kind of intermediate will be formed. Now if we rotate this bond like this, and draw it is in this manner. So you can see that the nitrogen can give the lone pair to this group, and by resonance it can attack to this carbon, and the sulfur, the positively charged, it will leave as this group, and there will be this formation of this kind of group, which after reacting with water or after hydrolyzing, it will give the N terminal peptide fragment, which is having a lactone unit, and the C terminal fragment, it will just cleaved. And so if we have a amino acid which have methionine, like if we have amino acid like M, a chain like if I draw A, then F, then S, then M, then R, then A. So it is alanine, it is phenylalanine, it is the serine, it is methionine, it is arginine, and it is also alanine. Somebody wants to join. Yes. So if our peptide chain goes like this, now what will happen if we add cyanogen bromide? Then it will cleave like this, and we will have two fragments like A, F, S, M, and another fragment R, A. So just remember, cyanogen bromide breaks peptide bonds which have methionine at the carboxylic acid side. Now this is the carboxylic acid side, and this is the nitrogen side, which is the you know this from the basic peptide bond sequencing. So that's how the fragmentation of the peptide bond happens. Now moving towards the next question. If you have any doubt regarding to any question, just write in the chat box. At the end of the session, I will answer those doubts. So the next question goes like this: which of the following statements are true regarding to the peptide bond? So when doing this kind of question, just read the question carefully, whether it is asking for the true statement or the false statement. So here it is saying that which of the following statements are true regarding to the peptide bond formation. So the options goes like this: the carbonyl is syn to the hydrogen of the NH bond. So the carbon of the so all of you, I hope all of you know the basic structure of the peptide bond. It is basically C double bond O and there is a NH. It is the structure of the peptide bond, and the question is deals with the orientation, how this peptide bonds is, the nature and orientation of this peptide bond. So the next option goes like this: the carbon nitrogen bond is purely single bond in character. We are referring to this bond. The F-MOXCl is used to form peptide bond. The hyperconjugation effect is reduced when hydrogen of the NH bond is replaced by R groups. So this is very easy question if you know about the orientation of the peptide bond, and it is a very important question because the orientation, the structure of the peptide bonds, it's basically the reason why the protein, how the proteins act, and what is the reasons. The stability of the peptide bonds depends on this kind of answers. Now I will show you the answer first. Yeah, so the true statements among these are the option D. The hyperconjugation effect is reduced when the hydrogen of NH bond is replaced by the R groups, and I will show you why it is happening, the structure of the peptide bonds. So yes, it is the resonating structure of the peptide bond. So like this, when I say about the peptide bond, it basically stays like this. The NH group, it is the first look at the first statement. It says this carbonyl bond is syn to the hydrogen of the NH bond, but actually it can be syn, it can be syn, it can be anti or cis or trans. But when it is trans, there is no there is a very good steric advantages of the syn anti form over the syn form. If it is syn, like if I draw the syn structure, that there is a carboxylic group and yeah. So if I say that the group is syn to the group, then how the structure will happen? It will look like this, and you can see there will be a steric repulsion between these. If it is NH group, and if when there is a R group, then the steric repulsion will increase. So always remember that the NH group, it stays in the anti form with the carbonyl group, and there is one more reason for that. If it is the C double bond carbonyl group, there is a bonding orbital here, there is a anti bonding orbital here also, which is the which is the sigma star anti bonding orbital of the carbonyl group. So this is a vacant orbital, and this NH group, it can give the electron density from this NH bond to this vacant site, and it is called the hyperconjugating effect. So when it is giving this electron density, the what happens that, so when it is giving the electron density, what happens that the stability of this peptide bond is increasing. That's why it stays in the anti form. That's why it stays in the anti form. In the syn form, this kind of sharing of electron density is not possible. Now the second option says that the carbon nitrogen bond is purely single bond in character. So it is not true, because you can see from this resonance structure, there is a lone pair of the nitrogen which can be donated to this carbon nitrogen bond. So it has a partial double bond character, and due to this partial double bond character, I will just draw this for once. So yeah, there is a lone pair here, and this lone pair is donated to this carbon nitrogen bond, and that's why it has a very partial double bond character, and is about 40% of double bond character in this carbon nitrogen bond. And due to this double bond character, the free rotation around the CN bond is not possible. So if you are given some option that if the free rotation around the CN bond it is possible or not, you can easily answer if you just remember that there is a resonance here, and due to this resonance, this bond is double bond in character, not single bond in character. And we know the double bonds are more rigid than the single bond, and free rotation around the double bond, it is not possible. And this option is false, you know, because F-MOXCl is not used for the formation of peptide bond. It is basically used for the protection of the amine site. And the last option, it is true that hyperconjugation effect is reduced when the NH bond is replaced by R. So as I said, if you replace this hydrogen with the group R, the hyperconjugating this donation effect will be affected, because when the group is R, there won't be many, this bond will be more stronger than NH, and it will not be easily giving its electron density. So I hope I am clear with this answer. So just remember few characteristics about the peptide bond, and from that you can easily answer this type of question if you remember just few characteristics of this peptide bond. Now this question requires you to answer which of the following statements are false. Now again I am saying, when answering this kind of true false question, just read the question carefully whether it is asking for you the false statement or the true statement. So the options are as follows. The enzymes are called artificial scissors for the peptide bond cleavage. The trypsin is highly selective for the peptide bond cleavage for the basic amino acid except arginine. The option C says that the chymotrypsin cleaves the peptide bond between the aromatic amino acid and the chymotrypsin cleaves the peptide bond between aromatic amino acid and other amino acid from C terminus N, and an enzyme with broad specificity is not suitable for the peptide degradation. So I will show you first the answer, then I will explain each and every option, so you are clear why it is false and why it is true. So the answer goes like this: trypsin is highly selective for the peptide bond cleavage for basic amino acids except arginine, and it is the false option. So I will discuss why it is false and why other options are true. So when you about the peptide bonds, when we learn the sequencing of the peptides bond, there are many enzymes which we use for the cutting the peptide bonds into smaller fragment to study their characteristic or to study why this is happening. And for that many enzymes are used. The examples of enzymes are trypsin, chymotrypsin. There is many other enzymes which are used, like V8 protease is one of the enzymes which are used for the peptide know the peptide bond sequences, and these enzymes are called artificial scissors. Now why artificial scissors? The scissor, we know what it does, basically it cuts the things. So that's because the peptide bonds, the long peptide chains are cut by the enzyme, they are called the artificial scissors. Now the second option, which is the false option, is the triplet. Trypsin is the highly selective for the peptide bond cleavage of the basic amino acids except arginine. Now the trypsin, it basically cleaves the carbonyls, the C terminal side of an amino acid which have a basic amino acid. Like if we goes like this, there is a peptide chain like A, there is F, there is R, there is S, there is M, and there is again there is W. If there is R is the basic amino acid which is arginine, and it will cleave them here, the C terminus N. Now there are three basic amino acid which are, one is histidine, and there is we have arginine, and and the third one is the lysine. Now these three are called the basic amino acid, and the basic amino acid basically used for basic amino acids, the trypsin cuts the peptide bonds for the basic amino acid except one amino acid which is the histidine. Now why it does not cut the amide peptide bonds having histidine? Because histidine has lower basicity than arginine and lysine. So that's why the option says that it will cleave the peptide bond having arginine, which is false, because it will cleave the it will not cleave the bond which is having histidine. So this option is false. Now the option C, it says that chymotrypsin cleaves the peptide bond between aromatic amino acid and other amino acid having a C terminus chain. So it is true, because chymotrypsin actually has a if you see the structure of chymotrypsin enzyme, it has a hydrophobic pocket which interacts with the hydrophobic interaction with the aromatic amino acids and cleaves the aromatic having peptide chain having aromatic amino acids. And the option D, which says that the enzyme with broad specificity is not suitable for the peptide degradation. It is also the true statement, because when the enzyme has a broad specificity means it will cut the peptide change at anywhere. So we cannot study that cleavage for the that is not useful, because it will cut at any space. We cannot just determine the sequence of the peptide change if we choose a enzyme which have a very broad specificity. And the example of this kind of enzymes are pepsin. So I hope I am clear with this question and the answer. If you have any doubt, you can write in the chat box. At the end of the session, I will discuss the problems or the doubts you are having. So moving toward our next option. So menifil resin is chloroformylated polystyrene, chloroacylated polystyrene, silicon dioxide, and polymethyl methacrylate. So what is the menifil resin? First I will just brief discuss about it. So the menifil resin, menifil gives is the name of the scientist which who basically, one second. So Merrifield is the name of a scientist who basically developed the technique of solid state peptide synthesis. And why solid state peptide synthesis is important? Because when there can be a solid state peptide synthesis and also solution phase, but when we are intended to synthesize a long peptide change, the solution phase synthesis is not that much feasible. So Merrifield he discovered that solid phase peptide synthesis, and for that we have a resin bed. Resin bed is basically a polymer bed which have a reactive site which will react with one side of the amino acid and give the, and then the sequential peptide bond formation will happen. Now first I will show you the answer and then we will discuss how it is happening. So the answer is chloroformylated polystyrene and the structure is like this. So the polystyrene, we know the what is the for the polystyrene, it is the polymer of vinyl group having, this is the structure of styrene, and the polystyrene, it has a backbone of like this and it has phenyl groups at the side chain. And chloroformylated means when this is reacting with formaldehyde and in presence of some HCl, it will have this kind of moiety which is called the chloroformyl moiety. Now when this is the resin bead which have this kind of functionality like this. Now when the peptide group, the amino acid it comes, we use actually FMOC protected amino acid for this reaction, and there is another reason for that why we use FMOC protected. There is a reason for that, and this is not about this question, so I will just skip that part. This carboxylic acid, it reacts with this side and then we have something like this. Now by this reaction the amino acids, okay, what happened I don't know, yeah. So while having this kind of reaction, the carbonyl basically the amino acid, it will be embedded on this. I am taking glycine here. The carbonyl amino acid will be embedded to this resin bed, and then when we can just deprotect this FMOC group and we can use another FMOC protected amino acid which will attack at react at this side, and we have the sequence of the amino acids, the peptide change. Now I said that we will take the FMOC protected amino acid. So basically why we do that, when we deprotect this group for after doing that first reaction, when we deprotect this group, it will generate one molecule which is called methynyl fluorine, which has a structure like this. So okay, and this is not looking that much. I will just, if you know the structure of FMOC chloride and you know the mechanism how the protection deprotection having, so you can know that after deprotection of that amino acid, it will generate this kind of molecule which is called methynyl fluorine, and this group is highly fluorescent. So we can monitor the peptide synthesis by doing by using this EPMA protecting group, that how many groups are there is attaching, how the reaction is proceeding. We can monitor that easily using this fluorescent property of this byproduct of the deprotection. So we use EPMA protected amino acid at first, and it will react with the chloroformylated part of this resin, and the sequential amino acids will be joined, and you can just remember that how the solid phase peptide synthesis happen. First it reacts, then the deprotection, and then again the coupling reaction happens. So I hope I am clear with this question. And now moving toward the next question, it says that which of the following derivative is formed in the Edman degradation of the polypeptide chain? Is it a DNP derivative, or a PTH derivative, or DCC derivative, or DNS derivative? Now when I was discussing a previous question, I shortly told you that what Edman degradation happens. Like if we have a peptide chain like this, there are many peptide bonds like C double bond O, NH. We will always have a free, if it is a non-cyclic peptide, if then we will have a free amine group at one side, which is called the N terminal side of the peptide chain, and a carboxylic acid group which is called the C terminus N. And the Edman reagent, what happens, that it reacts with, it is the phenyl isothiocyanate. If you remember that, it is I just showed you in the previous slide, that it is like something like this, and this reacts with this side of the amino acid and give a derivative from which we can know what was the N terminal amino acid. Now first I will show you the answer, and then we will discuss the mechanism. So yeah, it is the PTH derivative. So this PTH stand for the phenyl thiohydantoin, and I will just erase this part first. So just say look at the mechanism. There is a peptide chain, there is a free NH2 group. The lone pair will attack to this carbon of the Edman reagent. This is called the phenyl isothiocyanate or Edman reagent, and via the resonance this kind of structure will be happening, and it happens at pH 8. Just you don't need to memorize everything, just remember few little details of the mechanism. And after having this reagent, this kind of derivative, which is called the phenyl thiohydantoin derivative. For the if you know, somebody knows the structure of hydantoin, it looks like this. So hydantoin is basically a 5-member ring. This is the 5-member ring. It is called the hydantoin, which have a NH carbonyl group, again a NH, and again a carbonyl group. And it is called thiohydantoin because we have a sulfur in place of a oxygen. So it is called the and phenyl, because we have a phenyl group here in place of a hydrogen. So it is called the phenyl thiohydantoin derivative. When if it is not a Edman reagent, if it is a Sangus reagent, then the DNP derivative is formed, and if it is a dancyl chloride, then the DNS derivative is formed. And all these reagents do only one thing, they just tag the free and amine group side of the peptide moiety, and we can from this derivative we can know that what was the N terminal amino acid, because by seeing this group R, which is added to this PTH derivative, you can easily determine what was the N terminal amino acid. Suppose it was alanine, so we will have methyl at the place of the R. So seeing the methyl, we can say that okay, the N terminal amino acid was alanine, or just like that you can just answer this kind of question. So just remember that how which is the structure. Again I am saying you don't need to remember the exact mechanism, just remember what is the structure of advanced reagent, what is the name, and what is the derivative which forms. Now moving toward our next question, it says that which of the following is correct sequence of a hexapeptide based on the following statements. So there are few statements which are given, and based on the statement you have to know, you have to just determine what is the correct sequence of a hexapeptide. So the statements goes like this: the amino acid compositions are 2R, A, S, V, Y. The Sanger's reagent treatment will give DNPA. The trypsin digest, it give 2 peptide RAV, RSY, and the chymotrypsin digest give 2 peptide ARVY and RS. Now this abbreviation is the abbreviation for the amino acids. Now I know that it is a very tricky part, because you don't you have to remember few amino acids, but this some are easy to remember, like A, it stands for alanine, S, it stands for serine, V, it stands for valine. So, but there are some tricky amino acids like Y and R you need to remember, like R is arginine, it is a basic amino acid, and Y is the tryptophan, or the yeah, it is tryptophan. So it is the aromatic amino acid. So you need to remember just few few codes you need to remember. So I know this is a very little tricky part, but you when doing these kinds of questions, you will remember it eventually at the end of this course. And the Sanger's reagent, now we will just discuss each and every point, and we will try to correlate with this structure which answer is correct and which is not. So the first thing is given that it is after the amino acid compositions are 2R, there are 2 arginines, alanine, serine, valine and tryptophan, and there is Sanger's reagent, and the Sanger's reagent treatment, it will give DNPA. And DNP, now I have told you in the previous slides that what Sanger's reagent does, it basically tags the N-terminal amino acid. Now if you see the options, all of these are the N-terminals, and this is the C-terminal amino acids, because these amino acids in this peptide chain, it has a free carboxylic acid group, and these amino acids each have a free amine group. So the Sanger reagent gives DNPA derivative. So that what it means, that the N-terminal amino acid is our alanine. Now the 4 options, all the 4 options have alanine as their N-terminal amino acid. So from this option we cannot say that which is the correct sequence of the amino acids. Okay. So moving toward the next statement, it is saying that the trypsin digest give 2 peptides like RAV and RSY. Now what trypsin does, I mentioned in the previous slides, I am repeating it once more, that trypsin basically cleaves where there is a basic amino acid, and it will cleave toward the C terminal of the basic amino acid. Now you need to remember that that it cleaves to the 2 things, it cleaves to the basic site, the basic amino acid, and it cleaves to the C terminal site of the basic amino acid. And there is also a exception, like the basic amino acids are, we know, the histidine, arginine and lysine, and it will not cleave histidine because basicity of histidine is less, but it will cleave the arginine and the C terminal C end side of end of the arginine, and also the lysine. So in this amino acid composition, this R is the arginine, it stands for arginine. Now the trypsin will cleave to the right side of the amino acid, like if the sequence goes like that, it will cleave like this. Now seeing this, let's go discuss from the first option. It goes like this: if it cleaves to the C terminal side of the R, so it will basically give us 2 fragments, and one fragment will look like this, VR, and another fragment will look like this. But our option statement says that it will group 2 peptide having these fragments. But from the first peptide, if we do it trypsin treatment, it will give us these fragments. So this is not the correct sequence of the hexapeptide based on these statements. Now moving toward the next option, if it cuts to the C terminal end of the arginine, it will give us 2 fragments. One fragment is like this, A, V, R, and another fragment is Y, S, R. Now we can see that it just follows these option statement correctly, because we have 2 peptides, one have R, A and V, it also have R, V and R, we have this 3, and it is have R, S and Y. So we have 2 fragments having these 3 amino acids. So this may be our answer. Now the third option, it goes like this. If we cut the C terminal, so there is a R in middle of this, so it will also have a fragment like here, like this, at the C terminal end of the R. So from this we will have three fragments. One will have A, V, R, second fragment will be Y, R, and third fragment will be S. So this also does not follow our this statement, because we are having now three peptides, and one having 3 amino acid, one having 2, and one having only serine. So it is not also the correct answer. And the last, if we cut here, again it will cut the right side of the amino acid on the trypsin digest, and we also have like this kind of fragmentations, R, R, and S. So it is also does not satisfy the third statement of our question. Now we will so from these, from what it is looking like, this option B is should be the correct. Now we will just confirm it from the third statement, which says that the chymotrypsin digest give two peptides having ARVY and RS. Now what is chymotrypsin digest? It will cleave to the amino acids having aromatic amino acid at the C time. So chymotrypsin, basically it will cut to the having peptide change having aromatic amino acid, and it will cut to the C terminus. So from these amino acid, Y is the aromatic amino acid, and we have to see that if there is a cleavage, I will just change the color of the pen here. Yeah, so this Y is the aromatic amino acid, and if it is cleaving, if we do the chymotrypsin digest, it will cut here, and we will have two treatment. When doing having chymotrypsin, we will have two fragment. One we have A, V, R, Y, and another we will have S, R. So we can see easily that this option also satisfied our third statement, that the chymotrypsin digest giving two peptides. So from this thing we can say that our third option, it is the our second option, it is the correct option. So yeah, the answer will be B. It is the structure of the hexapeptide is AVY, AVR, YSR. So I will always suggest for doing this kinds of problem, just try to use the first options, first 3 to 4 options. If the, like I used these first 3 options for answering this question, and I just verified by using last statement for if my answer was true or correct or false. Now sometimes it we cannot say that by doing this, but this is the, if you follow this kind of rules, this is easier way to solve this kind of question. So just keep the last statement for the verification of the answer which you are thinking is the right answer. And this kind of questions are very important for the sequencing of the peptide chains. Now moving toward the next question. So it is saying that which of the following reagents are used for the peptide bond synthesis. So the options are HBTU, DCC, PIBOP, and all of the above. So we know the what is the peptide bond synthesis. I will just briefly. So if there is an amino acid here, we have a amino acid like say R1, and I am just giving you the brief about the synthesizing, and I will not going to the protection deprotection here. So let's say this side is protected, this amine group is not free, it is protected, and there is R2 here, and this is COOH, and this carboxylic acid also is protected. Now this reaction between these will give us the our peptide bonds. This will look like this. Now why these peptide bonds are formed? So it cannot just, if we just only mix this carboxylic acids and amines, there won't be any amide bond or peptide bond formation. We have to use some specific reagents for that, and these reagents are used for peptide synthesis. So the options are like this. Now I will show you the answer first. So the answer is all of the above. I will show you the structure of this kind of options. Like, okay, I will just erase this part. So yeah, So it is called the reagent HBTU, it is the reagent DCC, and it is the reagent PIBOB. So you do not need to remember any of this, only just you can remember the structure of DCC because it is important. Otherwise you don't need to remember just HBTU, PIBOB structures, just remember their names. So these are basically a benzo, there is a benzotriazole moiety, it is called the benzotriazole moiety, and these benzotriazole moiety have containing reagents are used for the synthesis of this peptide bonds, and these reagents I am telling that HBTU and PIBOB, these are more superior than the DCC because we cannot use DCC everywhere because DCC is not much reactive than these kinds of. So nowadays for peptide bond synthesis HBTU and PIBOBs are mainly used, but DCC also very good reagents for peptide bond synthesis and amide bond synthesis in general, and this just remember these names of these reagents and you don't need to remember the detailed mechanism. Yeah, you can remember the mechanism, how the peptide bonds are synthesized by using DCC only, and it is very easy mechanism if you see the lectures, and you can see that the mechanism is very easy. So remember the names and the mechanism, detailed mechanism for HBTU and PIBOBs are not required, just remember how the DCC is reacting. So basically after reacting with, basically we know that the peptide bond formation is between amine group and the carboxylic acid group, and while they react, and we will have elimination of water, and it will have this kind of peptide bond formation, and this water it will be taken up by this DCC, and after that we will have something called DHU, which is have a structure like this. So the name of this reagent is this intermediate is DHU, dicyclohexyl urea, and this is the byproduct of the peptide bond formation. So this water which is eliminated from the amine and carboxylic side of the amino acid, it will be taken up by DCC and it will form DHU, and that's how the peptide bond formation is happening. So you just remember this names of this the reagents and how the reaction is happening. Now moving towards our last question, the last problem of today's session. If you have any doubt till now, you can always write to the chat box. After the last question, I will answer your queries. So yeah, so read this kind of questions carefully, because it can be sometimes it can be some problematic. So a peptide with 12 amino acids has the following amino acid composition. It has 2 methionine, it has tyrosine, it has tryptophan, 2 glutamic acids, 1 lysine, 1 arginine, 1 threonine, 1 asparagine, 1 valine, and 1 cysteine. A specific cleavage of the intact peptide produces fragments with the following sequences: glutamic acid, cysteine, asparagine, methionine, arginine, methionine, glutamic acid, threonine, lysine, tryptophan, valine, and tyrosine. Which of the reagent was used for this specific cleavage? The option A is chymotrypsin, the option B is trypsin, option C is V8 protease, and option D is pepsin. So first, before doing this question, I will say briefly what these reagents do. So like previously I have said that chymotrypsin, it cleaves the amino acid chain at the C terminal of having aromatic amino acid. So when we have a aromatic amino acid, now by saying aromatic amino acid, there are 3 aromatic amino acid. One is phenylalanine, tyrosine, and tryptophan. So the structure, the phenylalanine, tyrosine, and tryptophan. So chymotrypsin will cleave a amino acid chain at the C terminus when we have these 3 amino acid present. Now trypsin, what trypsin does? Trypsin basically it cleaves having basic amino acids. So there are 3 basic amino acids, but it does not histidine, arginine, and lysine, but it only cleaves the peptide chain which has lysine, and arginine, but not histidine, because the basicity of histidine is very less compared to this, and again it will cleave to the amino acid at C terminal having this kind of amino acids. Now, what V8 protease does, it basically cleaves to the C terminal side of the acidic amino acids. Now, if we have acidic amino acid like glutamic acid or aspartic acid, then then it will cleave to the C terminal side of that amino acid. And pepsin we do not use for the specific cleavage of amino acid, because pepsin basically have a very broad specificity. So, because it has a broad specificity, it will cut the peptide change at anywhere it likes. It will not give us any specificity which we can use for the peptide sequencing. So, pepsin is not basically used for the peptide sequencing. So, option C is first ruled out, that pepsin will not be used because it is not specific. Now, so if we see carefully the structures, there is a site which have a arginine, okay, and it has a site having glutamic acid. So, it may be seem like that trypsin or V8 proteases can be the answer. Then we have to see the other options, like there are this kind of amino acid chain which has the aromatic site tryptophan, and it has a site of methionine. Now, and this is the last option, that we have a tyrosine and valine. Now, remember, like we have only used one amino acids and one enzyme, and we have 3 fragments. So, there must if you use trypsin, and it will cleave only at one side having arginine. So, there is only one arginine here present. So, if there is an entire peptide chain and we have only one arginine present here, so if it cut to the C terminal, we will have only 2 fragments. We will not have 3 fragments. So, trypsin cannot be the answer. So, the option trypsin, it is ruled out. Again, V8 protease, it also what it does, it cuts to the acidic amino acid group. But if you carefully see that there is no fragmentation at this glutamic side, or this glutamic side, it does not have any fragmentation to the C terminus. So, V8 protease was also not used, but there is chymotrypsin left. So, if you carefully see, there is a tryptophan this side and there is a tyrosine. So, if you have this kind of chain and we have a tyrosine here and a tryptophan here, and then it will cut to 2 sides and we will have 3 fragments. So, from these options, it seems like the chymotrypsin is the most likely to be the answer. Now, I will show you the answer. So, yes, it is the chymotrypsin which fragments this peptide chain, and that is why we have these 3. So, for answering this kind of question, you need to remember specifically that what these enzymes does, what chymotrypsin does, what trypsin does, and what V8 protease does, and then carefully look at the fragments and verify each and every using each and every enzymes, like which is most likely to be the answer. So, this was the last question of today's session, and I will now move to the part. So, now the session is open for question answer sessions. Now, if anybody have any question regarding to today's session, you can write in the chat box, and I will answer that questions. And if you have any question regarding to today's session, you can write in the discussion forum in the NPTEL website. You can ask the question here there always, and that site I will answer that question. So, I will stop presenting at first. So, the NPTEL site, there it has a option like ask the question, and there you can always ask any question if you have regarding to today's session. And this was the week 2 course. These questions were based on the week 2 materials and the week 2 videos, and this will help you for reference books and basic concept. So, there are for basic concept, there are some reference books are mentioned in the NPTEL website. The professor has mentioned it, or for reading this kind, you can use any kind of peptides bond, protein bonds basically, and I will share the names of the books in next class if you want. There is because I don't remember. And you can use actually the Google for reading this kind of things, because Google is always have many sites which have this proteins about this amino acids, and exact names I do not remember right now. I will share the names of the books in the next lecture positively, and you can just go through the course material for now. And if you have any these slides and today's video, I will share, it will be shared to you, so you don't need to worry about if you have missed anything. And this kind of problem solving session we will have each week, each Friday, for the next 12 weeks from 7 to 8 p.m. So I encourage you to join this problem solving sessions, because here the kind of problems we are solving you will have in your assignments, and doing this kind of problem will help you to do your assignments. And if you have any doubts regarding to session, you can always mail me, and I will just share my mail ID here. So this is my mail ID. If you have any query, you can just email me to this mail ID, and I think I can stop today's session. And thank you all for joining today's session. I hope I was able to help you in regarding to clearing some doubts regarding to this course. And now I will close the session, and we will meet next Friday at the same time. And meanwhile, go through the course material, and all the best for your week 2 assignment. Yeah, thank you all, thank you very much.